Okay, so on second thoughts, we decided to go back and do the examples after all, right? Because we just proved all those theorems, starting from the theorem shortest distance up until the very last theorem, which is the converse of the time chord theorem. So it would be very unfair if we leave it without showing you the application, right? You should know how to use those theorems. So that's what we're going to use now. We're going to try to apply them. So I think I'm going to do like 3 examples, and then you can do the problems afterwards, right? No problem. So I'll read the statements and then we answer the questions. So we're doing example 1, right? They are saying in the accompanying diagram, AB is the diameter of a circle and PCQ is the tangent to the circle at C. AC, CB, CD, and DB are drawn. They are telling you that angle C3 is equal to 42 degrees and angle C4 is equal to 33 degrees. Let's read that again. They are saying in the accompanying diagram, AB is the diameter of a circle, right? PCQ is a tangent to the circle at C. AC, CB, CD, and DB are drawn. They are telling you that angle C3 is equal to 42 degrees and angle C4 is equal to 33 degrees. So we have this diagram here, this circle here. Can you see the circle?
Yes.
They are telling us that AB is the diameter of the circle. If you are told in circular geometry, if they are telling you that some chord is a diameter, what comes to mind first of all when you hear that?
Oh, a diameter subtends 90 degrees.
Yes, you should know that your diameter subtends 90 degrees because each and every word like diameters, tangent, or circle, chord, it has a meaning. It tells you something. So if they're saying AB is a diameter, that means it subtends 90 degrees.
Yes.
Right?
Yes.
No problem. Then they're saying PCQ is a tangent to the circle at C. They're saying PCQ is a tangent to the circle where? At C. Can you see?
Yes.
No problem. If they're telling you that this thing is a tangent, what should come to mind is a tan chord theorem, right?
Yes.
That the angle between that tangent of yours and the chords is equal to the angle subtended by those chords on the other segment.
Yes.
Are you with me?
Yes.
Okay. They are saying to you now, AC, CB, CD, and DB are drawn. So these lines over here are drawn.
Yes.
They went on to say angle C3 is equal to 42 degrees. C3 is this one is 42 degrees. And C4 is equal to 33 degrees. There is C4 is equal to 33 degrees. Are you happy?
Yes.
So, question number 1, they're saying calculate the size of C2. Where is C2? C2 is this angle here. Are you with me?
Yes.
Part of this angle, it forms part of the angle that is subtended by a diameter. Because we said this is a diameter. Let me make this wavy line here. AB is a diameter. Are you with me?
Yes.
So we know that if AB is a diameter, it subtends a what? A right angle. So it subtends a 90 degree. So all angles that are formed by this chord of yours, special chord, which is the diameter AB,
Yes.
are right angles. So which means this angle here should be 90 degrees.
Yes.
Are you following me?
Yes.
So this angle here is what? Is 90 degrees. So what we can say, okay, this angle C2 plus C3 is equal to 90 degrees. Because this angle in a semicircle is an angle subtended in half a circle.
Yes.
And it's subtended by a diameter. Are you happy?
Yes.
So, we'll say, okay, we're doing A now, right now. A, we'll say, okay, C2, angle C2 plus angle C3 is equal to what? It's equal to 90 degrees. What is the reason for this? This is an angle in a semicircle. So it's an angle subtended in half a circle. So C2 is what we're looking for, right?
Yes.
So C2 plus C3, what is your C3?
42.
It's 42 degrees. It's equal to
90.
90 degrees. Therefore, your C2 is equal to 90 minus
48.
is 48 degrees. There is C2. Any questions?
No questions.
So, take that 48 of yours, C2, and put it back here. Each and every answer that you get, you should always put it back so that you know what you have and what you don't have. The moment you do that, you don't. If you don't, sometimes it's difficult to see the things or remember the things that you have calculated already. Are you following me?
Yes.
No problem. At B, they wanted to calculate the size of A. Right?
Yes.
They want to find the size of A. What is A? A is that angle over there. Can you see it?
Yes.
They want us to find the angle A. What is this angle subtended by? Where is it coming from? Angle A here. What is it subtended by?
It's subtended by the chord CB.
So your angle A is subtended by this chord here,
Yes.
CB. Do you see that your chord CB intersects with this chord of yours CB? It intersects with the tangent at C.
Yes.
Can you see that?
Yes.
So there is a tangent, right?
Yes.
There is a tangent PCQ. And you can say that your A is subtended by the chord CB. A is coming from CB. Can you see?
Yes.
Can you see that?
Yes.
And your CB does intersect your tangent there at C.
Yes.
So you have this angle here between the tangent and the chord, which is what?
33.
It's 33 degrees. This is what we just did, which is the tan chord theorem. We said that the angle between the tangent and the chord, right,
Yes.
is equal to the angle that is subtended by that same chord on the other segment. Because if you look at your chord, here is a chord CD. You have a major segment
Yes.
and you have a minor segment. So, which is the angle between your tangent and your chord will be equal to the angle that is subtended by this chord on the other segment, which is this segment on the other side. Are you following me?
Yes.
Are you happy with this?
Yes.
So in that case, we're going to say now our angle A is equal to angle C4, because the angle between your tangent again and your chord, right, which is the angle that is formed between the tangent and the chord, will be equal to the angle that is subtended by the same chord on the other side.
Yes.
Do you see that?
Yes.
So in that case, what do we say? We say, okay, one angle A, right,
Yes.
and is equal to angle C4, which is what?
33.
Which is 33 degrees. What is the reason? This is the tan chord theorem. This is the tan chord. We're done here. So what we have here is what? Is 33 degrees. To explain it again, here is the angle between here is your chord and here is your tangent. The angle between the tangent and the chord will be equal to the angle that is subtended by the same chord on the other side, on the other segment. Are you happy?
Yes.
Okay. Now, we move on. We're done with A, done with B, we're doing C now, D now, or C, finding D. What is D? Can you see this angle D here?
Yes.
Where is it coming from? It's coming from the same chord CB.
Yes.
Are you following me?
Yes.
Your angle D is subtended, which is subtended by the same CB.
Yes.
That same CB, that same chord CB, makes an angle of 33 degrees with the tangent, which is this angle here will also be equal to that angle
Yes.
because of the same tan chord. Because the tan chord says that the angle between the tangent and the chord will be equal to the angle that the chord subtend on the other segment. So, in that case, we can say, okay, angle D is equal to what? Angle C4, which is equal to what? 33 degrees. Why? This is a tan chord. Same theorem. Tan chord theorem, which we proved. Are you following me? And you could have said this and this are equal because these are angles on the same segment.
Yes.
Because they are subtended by the same chord,
Yes.
CB,
Yes.
or same minor arc CB. That's another way you could have looked at it. So we know that this angle here is what? 33 degrees. This is 33 degrees. Are you with me? So we're done with D. Now, go to C1. Where is C1? C1 is that angle over there. Are you with me?
Yes.
C1 is that angle over there. How can we find that angle over there? We can say, okay, C1 plus C2 plus C3 plus C4. It's called 180 degrees.
Yes.
Those are angles
On a straight line.
in a straight line, right?
Yes.
Or we know this angle is what? Is this entire angle is 90.
Oh, yes.
So we know this one. So we can find angle B.
Yes.
this angle B should be equal to that angle there.
Yes.
Because C1 is an angle between tangent, this tangent and chord AC.
Yes.
So this C1 should be equal to angle B.
Yes.
I think let's do it that way,
Okay.
which is consistent with what we're trying to prove. We all know angles in a straight line are supplementary. We've been doing that since the beginning of time.
Okay.
So, in that case, we say, okay, in triangle what?
ACB.
In triangle ACB, right?
Yes.
Say angle A plus angle B plus angle C is equal to
Let's go to
180 degrees. These sum of angles in a triangle, right?
Yes.
Your A is 33 degrees
Yes.
plus B, which is what you're looking for,
Yes.
plus C, which is what? 90 degrees. It's equal to 180 degrees. So what do you get? The angle B is equal to 90 minus 33.
It's 57.
It's 57
7.
degrees. Are you with me? So we get that angle B, which is this angle here. Let's say maybe B1 and B2. I didn't see that there were two of them. Let's say this is B1 and B2. Do you agree?
Yes.
So in that case, we say, okay, B1, B1, and B1. So your angle B1 is equal to 57 degrees. Are you with me?
Yes.
This, your angle C should be equal to B1 by a tan chord theorem, because the angle between the tangent and the chord is equal to the angle that this chord subtended on the other side. So in that case, what do we say? We say, therefore, your C1 is equal to angle B1, which is equal to 57 degrees. We can say this is a tan chord theorem. And we're done with the first example. Do you have any questions for me?
No questions.
Straightforward, right?
Yes.
No problem. So what I'm going to do now, I'm going to clean the board. After cleaning the board, we will move on to another example. Okay, so now we're doing example 2, right? In example 2, they're saying ACD is a tangent to the circle HC. AB is equal to AC. A1 is equal to 47 degrees. A2 is equal to 33 degrees. Not sure if you see this. Let me read this thing again. They're saying ACD is a tangent to the circle at C. So you can see ACD is a tangent to the circle there at C, tangent just there at C, right? They went on to say that AB is equal to AC. Can you see?
Yes.
If you look at ABC, what kind of triangle is that?
Which?
ABC
Oh, it's an isosceles.
is an isosceles if you have two sides equal,
Yes.
right?
Yes.
They went on to say that A1 is equal to 47 degrees and A2 is equal to 33 degrees. So they want you to do what? To calculate the magnitude of C1, F2, and angle E. They want to find those angles. Are you with me?
Yeah.
Okay, let's go. Where is C1? C1 is this angle here.
Yes.
Are you with me?
Yes.
Okay. Do you know anything about this angle?
Which one?
Angle C1, the one that you want?
Anything?
Yeah.
Angle C1 is equal to angle B.
Angle C1 is called angle B
Yes.
because you have an isosceles, right?
Yes.
So if you have an isosceles, two sides are equal, right?
Yes.
And the angles that are opposite those equal sides are also going to be equal.
Yes.
Because this angle is opposite this side and this one is opposite this side. So this one should be equal.
Yes.
Because those are angles opposite equal sides.
Yes.
So, what can you say? We're trying to find C1, right?
Yes.
We say in triangle A, B, C, right?
Yes.
Angle A1 plus angle B plus angle C1 is equal to
180.
180 degrees. What is the reason for this?
Some angle in the triangle.
Sum of angles in a triangle. Are you with me?
Yes.
But look, angle B is equal to angle C1 because these are angles that are opposite
Equal side.
equal sides. Are you with me?
Yes.
In that case, it's okay. A1. What is your A1?
47.
It's 47. Plus, instead of putting your B and C, you'll have two unknowns.
Yes.
You can just substitute your C, because B is equal to C. You can just put C1 here, plus another C1 as well. So this first C1 sits in the place of B, because they're equal.
Yes.
Is equal to 180 degrees. So 2C1 is equal to 133 degrees, right?
Yeah.
Divide by 2. Divide by 2. You get that the angle C1 is equal to 66.50. Can you check?
Yeah.
Okay. So in that case, we found that angle C1 and B, they're both equal, but they're equal to what? 66.5. 66.5. These are the angles. Are you happy with this?
Yes, I'm happy.
Okay. Now, we move to the next one, which is F2. They want us to find F2. Where is F2? F2 is this angle over here. Can you see?
Yes.
What can we say about this angle? Do you know anything that it is equal to?
Okay, let me check.
Where is it coming from?
C2.
It's coming from C2.
No, sorry. You are asking.
Where is F2 coming from? What is it subtracted by?
Oh, subtracted by CE.
It's subtracted by CE, right?
Yes.
What is CE? What is it called? CE. This line CE.
Diameter.
No one said it was a diameter.
Oh, it's a chord.
It's a chord.
Yes.
So, is there anything that is this chord related to our tangent? ACD, because ACD is a tangent. This, we're told that ACD is a tangent. This thing is a tangent here.
Okay.
Can you see?
Yes.
ACD is a what?
It's a tangent.
So, is your CD related to a tangent? Does it meet or touch your tangent?
Touch.
Yeah. Does your C, there's a chord CD intersect with the tangent?
Yes.
What? Yes, there E. So, now, if you can find what this angle is, it will be equal to that right hand chord.
Yes.
How can we find this angle?
Oh, C4
Mhm.
is equal to C1.
This angle here, C4, is equal to C1. These are vertically opposite angles. That's how you should look at this. So look at the angle. Where is it coming from? It's coming from this chord here, CE. Is it related in any way with the tangent? Yes, they're intersecting there. So the angle between the two is equal to that angle over there.
Yes.
The angle between the tangent and the chord is equal to the angle that your chord subtending the alternate segment. Are you happy with that?
Yes.
So what we'll say, okay, C1 or C4, angle C4 is equal to C1, right?
Yes.
And that would 66.5 degrees. These are vertically opposite angles. Are you happy with this?
Yes, I'm happy.
No problem. So we have this angle over here to be 66.5. But by tan chord, the angle between the tangent and your chord would be equal to the angle that this same chord subtends on the other side.
Yes.
Right? Therefore, F2 is equal to what? Is equal to C4. And that both equal to 66.5. This is a what? This is a tan chord theorem. We're done here. So we know that this angle here is 66.5. Are you happy?
Yes.
No problem. Now, we did A, B, now we're doing C. What do they want in C? At C, they want E, right? At C, they want what? They want this angle here. What is this angle? You can say this angle here, right? It is the interior angle of this big triangle. Can you see this?
Yes.
Or an interior angle of this triangle. Are you with me?
Yes.
Then how are we finding this?
You are saying E is the interior angle.
Of this big triangle over here.
Okay.
So we can find this because these are angles C2 and C3. We can find them. Because C1, C2, and C3, they make 180 degrees.
Yes.
They are angles on a straight line.
Yes.
Then you find what C2 and C3 are. Then when we add these, they should give us.
Yes.
Do you agree?
Yes.
Or what we can try to do, we can say, oh no, let's not try anything. I don't see anything else. Do you see anything else?
I think we can get F1.
F1.
We do have F2, right?
Uh-huh.
So if we can get F1, because we know that F1 and F2 is equal to 180.
Uh-huh.
They are angles in a straight line.
Yes.
And then after we got F1,
Uh-huh.
we will look at that triangle AFC, right? Then after we got F1, we will find C2. After we got C2, then
we'll have that exterior angle.
Yes.
Okay, I see that.
No, like tan chord.
Tan chord.
Yes. C2. No. Yes, C2.
Or if you find, you're saying if you find what C2 is.
Yes.
If you find what C2 is.
Yes.
This angle here will be equal to that angle over there.
Yes.
Now that one is even nicer because it's relevant to what we're trying to do.
Yes.
To this tan chord thing.
Yes.
So
let's get F1.
You want us to find F1?
Yes.
Okay. No problem. That even sounds better. So F1 plus F2. That will give us what? 180 degrees, right?
Yes.
These are angles on a straight line. Are you with me?
Yes.
And then now we know that F1 is what we're looking for.
Yes.
Plus 66.5 is equal to 180 degrees.
Yes.
Therefore, your F1 is equal to what?
113.50.
113?
Yes.
113.50. 113. Since 113.5.
No, it's 113.50.
It doesn't matter.
Okay.
No one cares about this here.
Alright.
So we have this point here. It is what?
It's
11.5. 113.50. That's what we have there.
Yes.
So you want us to find angle?
A C2.
Angle C2 in
Yes.
this triangle.
Yes.
Then that's saying this angle here will be equal to the angle in the alternate segment.
Yes.
I do agree, and I like this one better. So, what do we say? We say
Triangle.
in triangle what? Triangle
A.
ACF, right?
Yes.
C2 plus A2 plus F1. That will give us 180 degrees, right?
Yes.
This is sum of angles in a triangle.
Yes.
So C2 is equal to 33 plus A2, C2 is what we're trying to find.
Yes.
C2 plus A2 is 33 plus 113.5 is equal to 180 degrees. Therefore, your C2 is equal to, say 180 minus 113 minus.
S3 is 33.5.
Is what?
33.50.
33.50,
50.
right?
Yes.
No problem. Then, say this angle, this point here. We have what?
We have
33.50.
33.50. Yes.
So this angle here between the tangent
Yes.
and the chord is called the angle in the alternate segment.
Yes.
So you're going to say, okay, therefore, our angle E is equal to C2, which is equal to 33.50. Are you happy?
Yes.
The reason for this, we say this is a tan chord theorem. And we're done with these questions. We're left with one more example and we're done. Are you happy? No problem. So I'll clean this one if you don't have any questions. And then we do the last example and hopefully everyone will be happy as well. So let's go. They're saying AQ is a tangent to the circle at Q. Chords PQ and PB are drawn with PB produced to meet the tangent at A.
Okay.
Are you with me?
Yes.
They're saying AR is drawn parallel to QP. QB is drawn, right?
Yes.
They're saying prove that RA is a tangent to circle ABQ in A. Let's go step by step. That's saying AQ is a tangent to the circle Q. You have this line AQ. Can you see it?
Yes.
It's a tangent here at Q.
Yes.
Can you see that?
Yes.
Okay. Do you want me to highlight it?
Yes.
Let's highlight it with the red ink. AQ is a tangent here at Q. Can you see? Here's AQ. It is a tangent. If you have a highlighter, use a highlighter. They wanted to say that chords PQ and PB are drawn. We have chords PQ and PB. Can you see them?
Yes.
Sorry, chords PQ and PB. Can you see that?
Yes.
They are drawn such that your PB is extended to intersect your tangent here at A.
Yes.
Are you with me?
Yes.
They wanted to say that now AR is parallel to QP. Where is AR? AR is parallel to QP. Is that clear?
Yes.
And QB is drawn. Here is QB over here. QB is drawn. Here is QB. Yeah. It is drawn.
Okay.
I follow me. It's just a tangent. So they wanted to prove that RA is a tangent to circle ABQ at A. They're saying this line RA, which is parallel to QP, it is a tangent to circle ABQ. What is circle ABQ? Circle ABQ, do you say circle ABQ?
No.
Which means, let's suppose that there's a circle that passes through AB and Q. Then this AR is a tangent to that circle. So, you must draw that circle yourself so that you can be able to visualize it. Are you with me?
Yes.
So let's try to draw that circle and say, this circle ABQ, right? So it's a circle that passes through these points. So I'll say that circle looks something like this. Something similar to this. Of course, not perfect. But it passes there, and passes here. Do you understand?
Yes.
So that's saying that you must show that if there's a circle that connects these 3 points, show that this AR is a tangent to that circle at point A.
Okay.
Do you understand now?
Yes.
Okay. How do you prove that a circle, a line, is a tangent? I've shown you 2 ways of doing that. 1, you must show that your line of interest is perpendicular to the radius. If it is perpendicular to the radius at the circumference or at the outer point of contact, then your line is a...
Can you repeat again?
I'm saying, to prove that a line is a tangent to a circle, I said, when you're dealing with these things, show that that line is perpendicular to the radius. There was a theorem that I proved that a tangent is perpendicular to the radius at the point of contact.
Yes.
And then I went on to the converse, and I said that if there's a line if there's a line intersecting a circle such that at that point of intersection it is perpendicular to the radius, that line should be a tangent.
Yes.
I said that. That was the first thing I said. And then now, I also spoke about the time chord theorem, right? Yes. On the time chord theorem, I said that if a tangent intersects with a chord at the point of contact or at the point of tangency, the angle between the tangent and the chord would be equal to the angle in the alternate segment.
Yes.
Do you remember that?
Yes.
And then I went on to prove the converse, which is the opposite one, 9b,
Yes.
the last theorem that I did. Not the last one. The last one that I did was the cyclic parts. But 9a on tangents. So, I was saying that now. Another way of proving that a line is a tangent to a circle at a point, you use the converse of tan chord, right? Your tan chord theorem it states that the angle between the tangent and the chord is equal to the angle in the alternate segment. So the converse now, it says that if you have a line that intersects a circle, right? Let's say it intersects the outer end of the chord,
Okay.
right?
Yes.
You have this line intersecting this. Do you see this chord here?
Yes.
You have a line intersecting the outer end of the chord,
Yes.
such that the angle between the line and your chord, I'm not saying the tangent, now just this line and the chord is equal to the angle in the alternate segment, then that line is a tangent. Do you understand?
Yes.
Which means if the angle between your line AR and your chord, maybe AB, is equal to angle in the alternate segment,
Yes.
then That is the converse of tan chord theorem. You will have proved that your line AR is a what? Is a tangent. So we're trying to prove that AR is a tangent. No one said AR is a tangent. It's what we're trying to prove. So treat it as a line now. So the goal is to show that AR is perpendicular to the radius, or the angle between your line AR and the chord it intersects at the point where it crosses the circle is equal to the angle in the alternate segment. Which means what we have to prove here, you have to prove that your A2 is equal to Q1. Now the question becomes, how do you know which one to use? You don't have anything radius about the diameters. You have nothing about that. So you don't have much room to work around with. Do you understand? You don't have a lot of room to work with. So use what we have. Use what you have. Are you with me? So that's what we're going to do. What we want to try to prove. Let's show that your A2 is equal to what? Equal to Q1. Are you with me?
Yes.
Okay. It's up to you. You can start with A2 or you can start with Q1 and try to work with it. Which one? What do you want to start with?
Let's start by A2.
A2.
Yes.
So if you look at A2, A2 is this angle here between this parallel line
Yes.
and this line.
Yes.
And this line of yours intersect another parallel line there.
Yes.
So this line of yours is called what? This line AP?
Transversal.
It's a transversal.
Yes.
Right? It intersects two parallel lines.
Yes.
So you should know that by now
A2.
that I'm missing the red ink.
A2 is equal to
Use the red ink.
Look at your pockets.
No, it's not. Okay, so if we start with A2, you can say, okay, I shouldn't be using the red ink anyway. So here's A2 here is equal to angle P. Do you agree?
Yes.
These are alternate angles
Yes.
on parallel lines, right? So you can say, okay, my A2 is equal to what? Angle P. Why? These are alternate angles on parallel lines because your PQ is parallel to RA. Are you with me?
Yes.
No problem. So, what can you say about this one? Angle P. Look at the angle P. Angle P is subtended by what? By QB.
Yes.
Which intersects your tangent? Angle P is coming from QB. And the QB, your chord QB intersects your tangent at Q.
Yes. Yes.
So which means the angle here at Q1 is equal to angle P by your tan chord theorem.
Yes.
These two angles, this one and that angle is equal or are equal. Because the angle between the tangent and your chord would be equal to the angle that this chord subtends in the other segment.
Yes.
Are you with me? So in that case, we can say with confidence that angle Q1 is equal to angle P. What is the reason? This is tan chord theorem. Are you with me?
Yes.
P is equal to P, right?
Yes.
So therefore, your A2 is equal to angle Q1. It should be Q1 because Q1 there.
Yes.
Because if you're saying the left-hand sides, the right-hand sides of two equations are equal, so are they. If you're saying the right-hand sides of an equation are equal, so are the left-hand side.
Yes.
So you have shown that your A2 is equal to Q1, which means this angle is equal to that angle.
Yes.
So you can say now, therefore, your AR is a tangent to what? To circle. To circle what? To circle A, B, Q. Are you with me?
Yes.
You must give a reason for it. Why? Because the angle between your line, are you with me? What is your line? Your line is AR. Your angle between your line AR and chord. And chord, what is this chord? It's chord AB. Do you agree?
Yes.
Is equal to angle in alternate segment. So, in short, this thing, what I've written here, is the converse of the tan chord. So we have shown that the angle between the line of interest and the chord is equal to the angle that this chord subtends on the other segment. So this should be, AR should be a tangent. And we're done here. Any questions?
No questions.
Any questions?
No questions.
Then I'm done. And I'm hoping this thing is clear to the viewers. And I hope it makes sense to you as it does to all of us here. Thank you for watching.
Thank you.
Cheers.